All right, let's dive in. Today, we're talking about this incredible, invisible science that literally holds our entire world together, engineering statics. Now, I know what you might be thinking, the science of standing still, but trust me, it is way more fascinating than it sounds.
I mean, just look at a structure like this. Have you ever really stopped to think about how a bridge weighing millions and millions of pounds doesn't just, collapse? You've got gravity constantly pulling on it, wind pushing it, and yet it stays perfectly still. How is that even possible?
Well, the answer is a field called statics. It is the absolute bedrock of so much of engineering. And to help us get our heads around it, we're going to use this map as our guide. It's going to walk us through all the core ideas. So, you ready? Let's get started. So first things first, what is statics really? Well, if you're an engineer or you want to be one, someone who builds things like bridges, cars, airplanes, you name it, this is ground zero. It's the gateway to understanding how to design things so they don't move. Here's the official definition. Statics is all about bodies in equilibrium. That's a fancy word, but for pretty much everything we're talking about, it just means stationary, not moving, not accelerating. It's the fundamental science of making sure things are stable, safe, and built to last. Let me put it another way. The chair you're sitting on right now, the building you're in, they are masterpieces of statics. It's this silent, invisible force field of physics that's literally preventing our whole constructed world from just crumbling around us. Okay, so to understand how all this works, we need a few tools in our toolkit. And the very first tool, the absolute foundation, is learning to speak the language of statics. And that is the language of forces. A force, at its heart, is super simple. It's just a push or a pull. But for an engineer, that is not nearly enough information. Forces are what we call vectors. And this is so important. It means they have both a magnitude, that's how hard you're pushing, and a direction. Which way are you pushing? You need both to know what's really going on. Now, how do we measure these things? Well, engineers use a couple of different systems, and you got to be careful. There's a critical, absolutely crucial difference between mass and force. If you mix these up, well, that's how major disasters happen. In the SI or metric system, it's pretty clear. Mass is in kilograms, force is in newtons. But in the US, we use the British gravitational system where things get a little weird. Force is in pounds, but the unit for mass is something called the slug. And yeah, this whole pounds is force thing can be a huge headache, especially since we talk about our own weight in pounds, right? It trips up so many engineering students that it actually inspired a song. And you gotta love this line from it. Pounds are a force, not mass in our sight. If you're an engineer, that's a mantra to live by. To make this all feel a bit more real, let's use some great analogies. A newton, that's about the force you feel holding a small apple. A pound force is the weight of a box of butter. Now, remember the difference. A kilogram is the mass of a pineapple. And a slug, well, a slug has about the same mass as a medium-sized dog, like a corgi. Kinda helps it click, doesn't it? All right, so now we have our language of forces and we know our units. We are ready for the single most important concept in all of statics. This is the whole point, the quest for equilibrium. An object is in equilibrium when it's not accelerating. Simple as that. Now, technically, that could mean it's moving at a constant speed, but for the bridges and buildings we're talking about, it means one thing. It is perfectly, completely stationary. And the entire field, all those complex calculations, it all boils down to this one beautiful little equation. This is the beating heart of statics. That symbol there, the sigma, just means the sum of. So what this says is the sum of the forces equals zero. That's it. That's the whole secret. So what does that actually mean? It means for anything to stand still, every single force has to be perfectly balanced out by another force. Every upward push is canceled by a downward pull. Every shove to the left is matched by a shove to the right. They all add up to a big, fat zero. But wait, what if the forces are balanced, but the object still moves? Is that possible? Oh yeah, and that brings us to the next critical piece of the puzzle. We have to add a little twist to our story, quite literally. Just think about it for a second. Let's say you push on the top of a really tall bookshelf, and I push on the bottom with the exact same force but in the opposite direction. The forces are balanced, right? It won't slide anywhere. But you know what it will do? It'll tip right over. So balancing pushes and pulls isn't enough. We also have to stop things from spinning. The answer is a concept called a moment. And this wrench is the perfect way to visualize it.
When you use a wrench, you're not just pushing on it. You're applying a force at a distance from the bolt to create a turning effect. Engineers call it a moment. You probably know it by its other name, torque. So a moment is just our way of measuring a force's tendency to cause rotation. And the calculation is pretty simple. It's just the force multiplied by the perpendicular distance from the pivot point. And here's the kicker. For an object to be in true equilibrium, the sum of the moments also has to equal 0. All the clockwise spins have to perfectly balance all the counterclockwise spins. No sliding and no spinning. That's the goal.
Okay, let's put this all together. We've got forces, the pushes and pulls. We've got moments, the twists. And we have our 2 golden rules. The sum of the forces equals 0, and the sum of the moments equals 0. With just those tools, you can analyze pretty much anything that's designed to stand still. And once you know what to look for, you start seeing these principles absolutely everywhere. A simple C-clamp? That's a little statics machine. The screw creates a force that's perfectly balanced by the frame. A scissors jack for your car? You're using a small moment, turning the screw, to create a system of forces powerful enough to lift thousands of pounds. It's all just forces and moments in perfect balance. So the next time you walk across a bridge, or sit in a chair, or just lean against a wall, I want you to think about that invisible battle happening all around you. This constant, silent struggle between forces and moments, all held in a perfect state of equilibrium. And I'll leave you with this thought. Now that you know the basics, what invisible forces are you going to see?